In this video, I'm going to show how to transform functions graphically. So if we think about how we've graphed things up to this point, we have always set up a table x comma y. So for instance, if I gave you something like y is equal to 3x squared minus 5, we would set up an xy table. And that works, but it's slow and it's not very efficient, and it's really not the full picture. It's not giving us a great idea of really what's going on. So what we want to be able to do is take these numbers and figure out how they are affecting the graph of a simpler function or simpler graph in order to determine what the new graph looks like. That is the idea. And this is valuable to know how these things work because it's important to know how functions are set up, how they are working. That allows us to manipulate them more easily. So yes, a graphing calculator can take any equation, any function, you can plug that in and it'll show you what it looks like, but it doesn't show you the why. So if I give you an equation maybe that deals with profit and I ask you to manipulate it to get a different outcome, if you're just using the calculator can't do that for you. But if you understand what the pieces do, well, then you'll be able to go in there and tinker with the pieces or change the pieces to get the desired outcome. And so that is the value behind this. We want to understand what the pieces are doing, how these transformations work. Now, the first thing that we do need to start with is just knowing some basic figures. I think most of these you should have seen before. So in this video, I'm going to look at 5 basic functions: the x squared, the x cubed, the square root of x, the cubed root of x, and the absolute value of x. There are, of course, other basic functions, and you're going to learn some of those in this class, and you're going to learn some of those in other classes, like sine or cosine or logs or exponentials. But we want to understand the basic points involved in all of these functions, so that way if I see an x squared, I know right away what the basic picture looks like that I will be able to transform. So the x squared function is what we call a parabola. It is that U-shaped curve. And I do want to know that, but I also want to know a little bit more detail. I want to know at least a few points along the curve. And in my class, I'm always going to require you to show or denote 3 points. Notice I've shown 5 on this, and that's just to make sure that we really understand what's going on. And how do I understand where these points are coming from, or how would I get these points? I could simply set up an XY table. And I know I said the long-term goal is not to set up any more XY tables. That is still the long-term goal, but short-term, so we can get the basic pictures in our head, we're going to set up some XY tables. So with x squared, I'm going to plug in some values that balance on either side of 0, so -2 to 2. If I were to square -2, I get 4. -1 squared is 1. 0 squared is 0. 1 squared is 1. And 2 squared is 4. And so now I plot these. -2, 4. -2, 4 would be there. -1, 1, 0 is 0, 1, 1, and then 4, 2. If I do the same thing with the x cubed function, I've only shown 3 dots, but I'm going to go ahead and set up a table with 5 points just to really make sure we understand what's going on. So if I plug in -2, -2 cubed is -8, -1 cubed is -1, 0 cubed is 0, 1 cubed is 1, and 2 cubed is 8. So I can plot all of those points. I've just squeezed these in here, so that's why I haven't made the axes extend as far, but this is why the rate is increasing so much more rapidly than the x squared function. That thing's shooting off to the -8. By the time we get to -2, we better be at -8, and we have -1, -1, 0, 0, 1, 1, and then by 2 we'll be up to 8, somewhere up here. So I can do this for all of my functions. The square root function, squeeze that table in here. There I can't start at a negative. I can't take the square root of negative values, so I'm going to start at 0, go to 1 next. I could go to 2, but that'd be a non-exact value. That would be an approximated value if I were to find what it is in the calculator. So I'm going to jump up to 4, which does have a nice pretty square root. Could go to 9 next if we wanted to. So the square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, and square root of 9 is 3. So we can see that we have the point 0, 0, 1, 1, 4, 2. We're to go over to 9, 3, but again, just running off where I'm graphing. The cubed root of x, not to write out a table for this one, but we could take the cubed root of -8. That would be -2, way out here. Cubed root of -1 is -1. Cubed root of 0 is 0. Cubed root of 1 is 1, and then cubed root of 8 is 2. So again, we can see the pattern. And the absolute value is just taking all things and making them positive, not changing their values. But -2, for instance, would be a +2. -1 would be a 1. 0, 0, 1, 1. I've shown, I think, the point 3, 3 here just to give you another point of reference. So we do want to be comfortable with these basic 5 shapes. And when I say comfortable with them, I want to be comfortable with what shape they're making in terms of the parabola, or kind of the squiggle here, what I call the squiggle. We have that single curving arc. We have the squiggle that faces side to side, or it's pointing more side to side, and we have our sharp view for the absolute value. We wouldn't be familiar with those shapes, but we also want to be familiar with the points that are on them. And notice some of the points actually seem pretty similar. So for instance, the x squared and the absolute value of x, they share the points -1, 1, 0, 0, 1, 1, both cases. The shape around them is very different because the x squared is going to 2, 4 next versus the absolute value would be going to 2, 2 next. So they have the two different shapes. Also notice the x cubed and the cubed root of x have the same three inner points there, the -1, 1, the 0, 0, and then the 1, 1. But how it operates around them, very, very different. So we do want to be comfortable with the points and the shape. I am going to ask you to always show me those 3 points. You can show more if you would like. I'm going to ask for 3 in minimum, and we want to make sure that we're getting the shape around them. So if I were to ask for, say, the absolute value of x, and you drew a shape that had the 3 points correct, but then put a parabola, that of course would be wrong. We want it to be the b. That is going to be an important component of these transformations. So these are things that we just want to have memorized. We just want to know what their basic points are. Notice they all share 0, 0. And so 0, 0 is what I will call a lot of times the base point. They all share it. That's kind of where everything is being drawn from. The pattern or the shape around it differs for all these functions, and we do want to be comfortable with that so we can reference it very quickly when we go to do our transformations. So let's talk about transformations. The first things that we're going to look at are what are called shifts, or also sometimes just called translations. Shifts or translations. And we get these shifts through addition and subtraction. Notice we can have addition and subtraction of the x, or we could have addition and subtraction of the parent function itself. Now, this is using function notation, and the key here is the position of where that number is being added, subtracted. If that addition subtraction is occurring inside the parent function, that is going to be horizontal, versus outside the parent function, that is going to be vertical. Trying to just give you some ways to think about these. If we're doing something to the x, well, we know the x runs horizontal, the x-axis runs left and right. So that x, if we're attaching something to the x, of course it's going to be shifting us horizontally. If we're completing the parent function, we can always think of that as the y, or the f of x, and then subtracting something to it. Well, the f of x, the y, is the vertical axis. So we're applying a vertical shift or a vertical translation in those cases. I'm going to give you examples of all of these in just a few minutes. Now the direction of those shifts depends on whether it's a positive or a negative. And here's the key. Anytime we have horizontal motion, it doesn't matter if it's a shift or a stretch or compression, which we're going to see later on. Anytime we have horizontal motions, the x's are always backwards or always opposite of what you would think. X is always opposite. And that's just a helpful little thing to remember as we go through this video. The y's behave as expected. Because if I told you something like x minus 2 squared, you'd say, well, minus 2, minus would mean I'm moving to the left. But x's are always opposite, so it'd actually go 2 to the right. If I see something like x squared minus 2, I'd say, well, minus 2 should be making it less, it should be moving it down, and that will be exactly correct in the y's case, versus if it is x squared plus 2, I'd say, well, that should make it bigger, and it does. Why are the x's always opposite? I'm going to come back around to that, so don't lose that idea. I'm going to address that later on in this video. Last point here, horizontal shifts must always occur first. Vertical shifts must always occur last. That is going to be very important. We will talk about other transformations in a little bit, but these two things will always be true. Horizontal shifts always first before anything else that is occurring. Vertical shifts always last before anything else that is occurring. So we're going to do a few examples. For really all my examples, I'm going to ask for a couple things. One, I want to see that you state the parent function. I ask for these steps for a couple reasons. One, it's making sure that I know that you know what's going on, that you really are understanding all the components involved. But two, it is helping you set up the problem. It is helping you think about these things in the correct way and in the correct order. The second step, I'm going to ask you to list the transformations in the order in which they occur. And then finally, the last thing is you're going to actually do the graph. So graph labeling 3 points. Now, if I say to label 3 points, it needs to be clear to me where those 3 points are sitting. And so notice, trying to do these things on a computer, not perfect, right? I kind of hand sketch these things with a computer. It's pretty clear that that's on the 1, 1. And so if it's pretty clear where they are falling, that is fine. As I go to graph things by hand, if it's unclear to me, especially without graph paper, if it's unclear to you or to me, then I need to graph those points because I need to see where all those points are actually falling. So let's start with 2 examples kind of at the same time, because I want to show you really the difference between when something is a horizontal shift versus when something is a vertical shift. So let's start with that x squared function. So the first one I have x plus 3 squared, and then I have x squared plus 3. Very similar numbers, very similar parent function, same parent function in fact, but the position of those numbers is causing a difference here. If we look at the position of the 3 at first, it is inside. It is attached directly to the x. So that is going to be a horizontal shift. Versus the plus 3 that is on the outside. We have the x squared, we've completed the parent function. The plus 3 is occurring outside, it's occurring on the y. That is a vertical shift. So that is one example of how we can see a difference between the two. Let's actually answer what I asked for. I asked you to do 3 things. I asked you to name the parent function, then the transformations, and then we'll actually do the graph. So for this first one, the parent function is the x squared function. You can write that a few different ways. You can write the x squared, you can write the squared function, or you can actually indicate to me what the graph looks like. I don't actually mind how you indicate this. I just want to make sure that you are understanding the first function that you're starting with, or what the initial graph is supposed to look like. Second, what did we say, what type of motion we have? We have a horizontal shift, but I want to be a little bit more explicit. I want you to tell me the amount and the direction that that shift is going. So this plus 3, it is horizontal, so that means left or right. And if I think about a plus 3, we have to go the opposite direction as we would expect. That means I'm actually going to the left by 3. So again, I want to see the direction and the amount. If we were to think about the other equation, the y equals x squared plus 3, again, we have a plus 3, that is our amount. The direction in this case is going to be up because this is a vertical motion. So up by 3 or up 3. And then we're going to get to the graph. I'm going to show you a couple different ways to approach doing these graphs. And the first is the kind of the graphical approach. So what I'm going to do at first is I'm going to graph the function that is not actually our answer. I'm going to graph the x squared function. X squared has 0.00, negative 1, 1, and positive 1, 1. And it would connect these 3 dots on that curve. But of course, with our function, the f of x, we said we had to go to the left by 3. So I'm going to go left 1, 2, 3. I'm going to take every single dot here and shift it to the left by 3. Let me clean that axis up for 1 second. So this point is going to go left 1, 2, 3. This point is going to go to the left 1, 2, 3. This point is going to go to the left 1, 2, 3. And now I'm going to connect the dots using the same pattern. It is still a parabola. We can see that it looks the same, it's just been shifted over to the left. So my points would be negative 3, 0. This would be negative 4, 1. And this would be negative 2, 1. And that would be my final image. Notice I've used kind of a color code here. It is always important to note what your final function is. So this was my final function, f of x in black. You can write a final next to it or the answer or whatever you want to do. In some way, it's got to be clear to me. If you're plotting multiple things on one grid, it needs to be clear to me what the final answer is. If I can't tell between these two, I'm not going to assume the right answer is true. I'm going to assume that you're not sure. So please do always indicate to me that what your final answer is. Now, I told you I was going to give you a couple different ways to approach these problems. So this works every single time. We can take these things and we can shift them physically on the graph. Doesn't matter how many steps we have, that will always work. Another way we can figure this out is by setting up a transformation table. Now, I'm not going to be setting up an XY table. I'm not going to be setting up X's and finding the Y's for it. That was the old method. What I'm going to do is actually set up a table of points. And so I'm going to do the second one kind of using that second method. So XY table for my X squared. My X squared XY's, we had the point negative 1, 1, 0, 0, and 1, 1. Those were those same points that we had in this blue function over here to the left when we did our graph. We just put those points on a graph rather than in a table. Then my transformation tells me I need to take each of those points up by 3. Well, if we think about what that's telling us to do, saying y plus 3. So I'm going to add 3 to all my y's, negative 1, 4, 0, 3, and then 1, 4. And so these are the new points that I need to be plotting. Negative 1, 1, 2, 3, 4, 0, 3, and then 1, 4. I know how the points behave around that. That would be my image. So there's good and bad to these two different methods. I don't care which one you use. You might use different things on different problems. I think the kind of graphical approach where you're actually shifting every number is more intuitive. It makes more sense. We can physically see those numbers and those points moving around. We are only doing one step right now. There will be problems that have 4, 5, 6 transformations on them. We can see that it's going to get very messy very quickly. That is the advantage of the table, is it's storing all that information in a very clear, concise way. We only end up with that one picture. It is a little bit more writing, maybe takes a little bit more work on the front end, but maybe a little bit easier in the back end. So it is a trade-off, and I think both have their times and places. The third method that you can use is the hardest. You don't have to necessarily set up a table or graph every single point. It is the hardest to keep track of. If you're really, really comfortable with the transformations, with all the steps, with all the different parent functions, then maybe you want to think about using this approach. But I'd say for 99% of you, you want to stick to one of these two methods at first. And the third method is just kind of hold all that information in your head. So for instance, if I were to take that first one, let me move this over. If I were to take that first one, I'm saying, well, I'm starting with the x squared function. That's my parent function. I need to shift it to the left by 3. So I'm going to move my base point to the left by 3. The base point, remember, is what I call 0, 0. I know they have that in common. 0, 0 is also unaffected by things like stretches and compressions. And I also know how the function works around that. It goes up 1 over 1 both sides. That is true as long as we don't have any sort of stretches or compressions. And so we get the same graph. If I were to take the x squared plus 3, same idea, moving my base point up by 3. I know how the function behaves around that, up 1 over 1 on both sides. And so I get my graph. This becomes much more challenging when I have a couple different shifts. I have a stretch, I have a reflection, I have all these different things going on. I've got to do all that in my head. I've got to process it all that in my head and process it in the correct order, because order does matter. And so that is much, much harder. I would recommend, until you really, really get super comfortable, set up a graph or do multiple graphs and then set up a table. Let's do another example. Let's take y is equal to the square root of x minus 1 plus 2. And so we're going to go through the steps. The first thing I want to do is identify the parent function. Well, the parent function is that square root function. Square root, or you can just indicate it as the square root of x. I don't mind how you indicate that. We should know what that looks like. It has the point at 0, 0, and it goes as the single ray from there. If we think about our second thing that I'm asking you to do, to list the transformations in the order that they occur, here I can see I actually have multiple numbers being added and subtracted. That means I have multiple steps. I'm going to have 2 different steps. So order matters. Now, there are problems that you can get away with listing things in the wrong order. It won't actually affect it. But there are a lot of times when the order does matter. So every single time you do a transformation, I want to see that the order is correct. Even if it doesn't affect the graph, if you write this order wrong, I'm going to take off points. So the first thing we always need to consider are horizontal shifts. The horizontal shift here, the inner function, x minus 1, that tells me to go to the right by 1. And then the outer thing, the plus 2 at the back end, that is telling me to go up by 2. So those are my steps in the correct order. Horizontal shifts first, vertical last. Now I'm going to do my graph. I'm going to do this both ways. I'm going to show you the table approach and the graphical approach. So the first thing I'm going to do is I'm going to start with the square root of x function. I'm going to use different colors to indicate my steps. And the square root of x has the point 0, 0, 1, 1, and 4, 2. So this would be my square root of x. First thing I have to do is go right by 1. I'm going to take every single point, shift it to the right by 1. And so now I have this picture. Just shift it over to the right. And then last, I'm going to, let me put it in black since it's my final image. Last, I'm going to shift it up by 2. So this point here is going to jump up 1, 2. It's going to come up here. This point right here is going to go up 1, 2 right here. And finally, this last point over here, it's going to go up 1, 2. That puts it right here. So connecting my dots, there is my graph. Notice it is important to note where that starting point is with square roots. Square roots do not continue infinitely in both directions. It is always a good idea to keep track of that 0, 0 because it doesn't matter if it's a square root where it's only proceeding from that 0, 0, or if it's x cubed where it's kind of bending around that 0, 0, it is a good idea to track that 0, 0. So the black curve is my final image. I am done. Just to see how the table would be set up. So square root function has a point 0, 0, 1, 1, 4, 2. Notice the same points that I identified when I drew out that first blue shape. From there, I'm going to go right by 1. That means I'm going to do x plus 1. It's 1, 0. Then we'd have 2, 1, and 5, 2. That would be the green graph. And last, I'm going to go up by 2, which means y plus 2. So 1, 3, 2, that was a 0, not a 1. I can't read my own writing. 1, 0, so I go up by 2, I get 1, 2, then I get 2, 3, and then I get 5, 4. So if I were to plot these points, 1, 2 is that point right there, 2, 3 is that point right there, and then 5, 4 would be our last point right there, which I need to really make a little bit clearer. So we do get to the same exact curve. We get to this final image right here in black. So two different approaches. Why, if we're setting up a table again, are we doing this new approach and not just setting up the XY table from before? Well, the challenge about the XY table is when we get really messy functions, really long functions that have, say, a 2x minus 1 squared plus 3 times another negative 1, whatever it is, right? We don't always know where it transitions, that curve transitions. With the x squared, we know it has that bend, or with a cubed root or x cubed has those bends. So if we're just plotting x negative 2, x negative 1, x equals 0, if we're just plotting this every single time, we might only see a section of it that doesn't actually show us where it's bending. We might not see the full picture. And so that's the risk of just plotting those random points. This is much more efficient. We are pinpointing where the excitement occurs, where that 0, 0 occurs. We're looking a little bit either side of it, and we're seeing that bend even after we've transformed. Plus, we're just understanding how the thing is being shifted. All right, the next thing we're going to look at are the other transformations. We're going to look at vertical shifts, vertical stretches, vertical compressions. So let me copy this over and we will take a look at this equation. I'm going to step through these a little bit slower too, but I'm going to throw up this really ugly looking equation at first. We'll talk about that and I'll break down what the pieces are. So if we have a parent function, f of x, and we're doing things to that parent function. We've already talked about the c and the d. Now, c has a 1 above it because that's our horizontal shift. That has to occur first. The d has a 4 on top of it because that is occurring last in our list. That is our shift up and down. So 1 and 4 we have already addressed. Let's talk about the a and the b next. A and b are simply constants that are being multiplied. Once again, position dictates whether they are vertical or whether they are horizontal. Something on the outside of the parent function is doing it to the y, that is vertical. Something on the inside of the parent function, that is occurring to the x, so that is horizontal. So we see a is vertical, b is horizontal. Just like with our shifts, vertical occurs like we would expect. So if I said 5 times the number, you'd say, hey, it's making it bigger. Well, it does cause a stretch if that a is greater than 1. If that a is less than 1, it is causing a compression. And when I say less than 1, that is ignoring the negative. So really, if you want to, put absolute values around these a's and b's. Miss that one a little bit. But if the a is a -3, the important part there is 3. The negative is really causing something else. We'll talk about in just a second. So look at the number and ignore its sign. If that a is greater than 1, so -5 or 6 or 18, that is a stretch. It's making it bigger. If it's 1/3, 1/2, 2/8, 9/74, those are all things that are going to cause a compression that's going to shrink it down. You may also see a stretch called a compression called a shrink. If we look at our b is attached to the x, so that means it has to be opposite. If the b is greater than 1, we would say, well, 2 times the number would make it bigger, but actually with horizontal, it's going to do the opposite. It's going to compress it. And if the b is less than 1, and again, we mean the absolute value of b here, if that is less than 1, then it's going to actually end up being a stretch because the x's are always backwards. Notice I say here what we're doing inside to the points as well. So if the c is attached to the x, we're actually subtracting that c from each coordinate on the graph. On the b, we're dividing, even though it says b times x, we do the opposite. We divide the x coordinates by the b. And then the y's behave like we would expect. So the d, we add that to the points. And then the a, also the vertical motion, we are multiplying that exactly as we would expect. Then the last sort of transformation we have is what's called a reflection or a flip. You might also see these called flips. There's a negative in front of the function that is going to cause a reflection about the x-axis. Negative in front of the x causes a reflection about the y-axis. And you might say that's a little bit backwards. If there's a negative on the y, wouldn't we expect it to flip over the y? Negative on the x, wouldn't that flip over the x? Let's think about this. Let's take just a single point. We'll take the point 2, 1. And let's say I make the x negative. So we'd make the 2 negative, and we'd have -2, 1. Which axis did we just flip over? We flipped over the y. So by making the x negative, we actually cause a y-axis flip or a y-axis reflection. Versus if we take that point 2, 1, and then we make the y negative, that actually causes a x-axis flip. So it is kind of backwards, but it's backwards on 2 fronts in a way, right? We do exactly what the problem tells us to. We make the y negative, we make the x negative, but that causes a reflection about the other thing. Okay. So to boil these down a little bit, to boil all these rules down a little bit, if we see addition or subtraction, those are our shifts. If we see multiplication or division, because remember all division is multiplication by the reciprocal, those are stretches / compressions. Shifts can go left or right. Stretch compressions affect the horizontal and the vertical as well. If we have things occurring inside the parent function, if we're doing it to the x, x's are always backwards. And then if we have negatives sitting in front of the parent function or the x, those are reflections. Okay, so we need to think about first off, do we have addition, subtraction, multiplication, division, or do we have a negative? and then is it attached to the x, is it attached to the y? Remembering x's are always backwards, they're always opposite. I will point out one more thing here, which is that I have given you an order. The key is really the most important things. Horizontal shifts must occur first, vertical shifts must occur last, same thing as I said on that very first page. The inside stuff doesn't matter as much. We do tend to think about multiplication happening where we care about the inside of the parentheses first, which is why I do have the, we can think about horizontals occurring first, but it really doesn't matter if we have all the shifts in the correct spot. So let's do a couple examples here. My goal is to do the same thing. I'm going to denote the parent function. I'm going to list transformations, and then I will do the graph. So I'm going to do two examples to start with to show the difference between the vertical and horizontal. So I see y equals 2x in parentheses squared, and I see a y equals 4x squared, the x just being squared in that second case. In both cases, our parent function is the x squared function. In this first example here, the 2x squared, that 2 is inside the parent function, so it is definitely a horizontal something or other. And because it is multiplication, it's going to be a horizontal stretch compression. We need to choose the correct one. 2x, we would expect the 2 to make it larger, but remember x's are always backwards, so it's actually going to be a horizontal compression by 2. This next example, y equals 4x squared, that 4 is outside, it's attached to the y. The y's behave exactly as we would expect. So that is going to be a vertical stretch. So notice my first step is always identifying, is it horizontal or vertical? We did the same thing with our shifts. And then based on that horizontal or vertical, I can figure out whether it's a stretch or a compression. I'm going to take the graphical approach on both of these just to have a consistent method for these two problems. So I'm going to start by graphing the x squared, same way I did before. I'm going to do it in blue, so x squared. Let me try that one more time. I didn't hit my mark very well. So these would be my 3 points here. That would be my x squared function. And then if I horizontally compress it by 2, that means I'm taking my x's and I'm dividing by 2. Remember, we do exactly the opposite of what it says. It says 2x, we're dividing by 2. So 0 divided by 2 stays 0. But then 1 divided by 2 is 1/2. Negative 1 divided by 2 is negative 1/2. So we end up with this graph right here. Let's take the 4 to the x. So I'm going to start by looking at that x squared. And once again, I have 0, 0, 1, 1, negative 1, 1. And let me do a better job because I know what this is going to look like. Let me move these around a little bit. Just tighten up my axis a little bit. So 1, 1, 1. And so we have our parabola, same idea as before. But now, because I have a vertical stretch, and I should note that it's a vertical stretch by 4, I do want to state what I'm doing and by how much. Well, that tells me to take my y's and multiply 4, exactly what it told me to do here, 4 times the y's of the parent function. 0 times 4 is still 0. This y value is 1 times 4 is going to give me 4. And then this 1 times 4 is also 4. And so what I see is I have this curve, and that original blue one I maybe made a little too steep. Let me try and spread that a little bit more accurately. Because we should notice that it has gotten steeper. That was the whole point. It's vertically stretched by that factor of 4. I know I'm not doing this on graph paper, so it's hard to see exact, but if we look at these two images, they should actually look pretty similar. We've taken these kind of more sweeping blue curves, we've got them more narrow and a little bit taller in the middle. They both look the same. There's a reason for that. 2x squared, I could simplify that. 2 squared is 4, x squared is x squared. It's 4x squared. These are the same. Why did I do this? Because I want to illustrate the reason we are doing the x's backwards. We're not really supposed to be graphing x's. If I think about any function, x is the independent variable. Why f of x is a function on x? X isn't a function on y. The x is the set thing to begin with. So when I'm trying to approach these problems and saying, well, we're shifting our x's left, or we're shifting our x's up, or right rather, not up, but right. We're compressing or we're stretching these x's out or in. No, we're not. The x's are what they are. They occur regardless. We're doing things to the y. Now, is it easier to talk about making those points move left and right rather than trying to figure out what the y is doing based on that? Absolutely. It's absolutely easier to say, well, we can think about taking this initial image and shifting it left or right. That is by far easier to do. But we're approaching the problem backwards. We're not doing anything to the x's. The x's are occurring no matter what. The y's are what we're trying to graph. So if we're trying to look at it from the standpoint of x, we're looking at it backwards. So we better do everything else around that backwards. We could take every single problem if we wanted to. It doesn't matter if it's a x squared or a square root or a cubed root. We could take every single problem and say, well, I could write this instead as the square root of 3 times the square root of x. And now I have a vertical stretch by the square root of 3 rather than a horizontal compression of 3. But it's much easier to view it in terms of a 3 rather than a square root of 3. So that's why it's easier to view things in terms of those x movements rather than just always strictly trying to look at things as functions on y. So that's a little bit of the why they are working like they are. Let's take another example. Let's look at f of x equals the absolute value of 3x plus 1. So this time we have a different parent function. The parent function is our absolute value of x. We do know that gives us a sharp V shape. Next, I'm going to list out the steps in the order in which they will occur. And I see that I have two steps here. I have a plus 1, and I have this times 3. Both are occurring inside the parent function, which means they're both horizontal of some sort. And I need to make sure I get that order right. This is a case where it does matter the order. Do I need to do the horizontal shifts first or the horizontal stretches compressions? Always horizontal shifts. So I have that plus 1, that's actually going to shift me to the left by 1. The 3 times x, that is actually a horizontal compression because again we're thinking of it as the opposite 3 we would think would make it bigger, but it's going to make it smaller. Horizontal compression by 3. And so here are 2 steps. I'm going to start by doing this one graphically, and we're going to see how graphically we can kind of get it a little bit tied up. It gets messy. So if I think about the initial absolute value function, it goes through 0, 0, 1, 1, negative 1, 1. It's the V. First thing I do, left by 1. So come here, this point comes here, and then this point comes here. So there's everything shifted to the left. Now I'm going to compress everything in by a factor of 3. So this is now the point negative 1. 1/3 of negative 1 is negative 1/3. This is negative 2. A third of negative 2 is negative 2/3. 0 stays 0. I've already gotten that in the wrong place. Get that red dot out of there. It should be there because it still has the same height. And so now if we connect those red dots, we end up with this very sharp V in here, and this red image would be our final image. Now, as you saw, I made a mistake because I got a little bit lost in my own points and my own arrows. And I think it's even worse if you're only using one color. If you're only using a single color, it's really hard to tell what is a line, what is the point, where are all these things going. And so this would be an example where I think it probably becomes a little bit easier with a couple steps to set up the table. Let's just see how that table would work. So the absolute value of x, our points were 0, 0, negative 1, 1. I haven't necessarily done these in order, and I like to list that 0, 0 first a lot of times because, like I said, that's that base point. It's important to keep track of it. It's where things are hinging off or bending off. So if I go left by 1, subtracting 1 from my x, so we'd have negative 1, 0, negative 2, 1, 0, 1. And then I'm going to have a horizontal compression by 3. That means I'm multiplying 1/3 to my x, or I'm dividing x by 3. It doesn't matter how you write that. So negative 1/3, 0, negative 2/3, 1, and then 0, 1. And those are exactly the points I plotted in red. Negative 1/3, 0, negative 2/3, 1, and then 0, 1. You can see that that is the same image, just if I hadn't done it with all the other points, it would have been a little bit clearer. Let me also stress one thing to you. When I ask you to write out those order of operations, this does not count. If you are using the table, which is fine, this is not enough to show me. I want to see the words. I want to see what things are doing. I don't just want to see the x minus 1 or 1/3 x, or I want to see that you're calling them shift left, shift right, horizontal stretch, horizontal compression. I want to see those words telling me what is going on. This is also a good example of how if I were to do things in the wrong order, I don't get the right picture. Let's say I'd done the horizontal compression first, and then I do my shift left. So I'm going to start with my absolute value. I'm going to go ahead and compress it first wrongly, so that compresses in, it becomes 1/3, that stays 0, that becomes 1/3. So there's my image, and now I'm going to shift it to the left. I didn't mention that was left, but it should be shift left by 1. And so that's going to come here. This is going to go over to -1 and 1/3. I pointed to the wrong point, the green. And then this green point is going to come over here to -2/3. Notice before, our vertex was at -1/3, 0, not -1, 0. So we've ended up with the wrong shape. And they can be off by even further. They can be in the wrong quadrant. They can be pointed the complete wrong way. So it really is important that we get that order correct. The order absolutely matters. Let's take another equation. Let's call this one g of x just for a little variety. -x plus 3 cubed minus 5. So the first thing I'm going to do is identify the parent function. That is the x cubed function, which remember looks like that. Next thing I'm going to do is write down the steps in the order in which they must occur. I do see that I have three things here. I have a negative thing in front of the x, I have a 3 here, and I have a -5 here. First thing is always a horizontal shift. Do I have a horizontal shift? Well, horizontal shift would occur inside the parent function. It would be a plus or minus. I do have a +3 in there. So that tells me it's going to the left by 3. Next, actually doesn't matter the middle a whole lot. The key is I have to have the last thing as my vertical shift. So a lot of times what I'll do if I'm listing steps, if I don't know how many there's going to be, I'll put a 1 and I'll put an L for last. The last thing I'm going to do is that -5. That is going to go down 5. Now, there is only one middle step, so step 2. Step 2 would be that negative thing in front of the x, so that'll be a reflection over the y-axis. So I've listed out my steps. Now I'm going to graph, and I'm actually going to set the table up on this one just to, again, spread things out a little bit, make it a little bit more clear. So now x cubed has a point 0, 0, -1, 1, and then 1, 1. The first thing I have to do, left 3 tells me to subtract 3 from all my x's. It's exactly the opposite of what it initially told me to do. So I'd have -3 is 0, -4, 1, and then 2, 1. Nope, try that again, -2, 1. Next, I'm going to reflect over the y-axis, which means I'm making the x's negative, exactly what the problem told me to do. Notice it had a -x there. So this is going to turn into the point 3, 0, 4, 1, and then 2, 1. And then finally, my last step is to go down by 5. So that's going to be y minus 5. Notice how I labeled my steps in my work. That is just to help me. I think it's a good idea. One of the reasons I do that is because then if I accidentally forget something, I get to the end of my table and I say, all right, I'm on step 3. Wait a minute, I was supposed to have a step 4. Then you can get back and fix it. So I think it's helpful just to label those steps to keep you on track of what you're supposed to be doing. So I have 3, 0 minus 5 is -5. 4, and then 1 minus 5 is -4. 1 minus 5 is -4 again. And good indication here that I've done something wrong, but let's graph it and we'll talk about why I've done something wrong and we can go back and correct it. So happy accident here. I did make a mistake and hopefully a lot of you have caught that, but let's see why I've made a mistake. So I'm going to graph my points. 1, 2, 3, 1, 2, 3, 4, 5. There's my first point. 4, -4, and then 2, -4. I know this is my old 0, 0. That's where things hinge from. That's got to be the center of my image. But remember, we're graphing the x cubed. The x cubed is supposed to look like this. So yeah, it might reflect, it might get stretched around, but those ends are still pointing opposite directions. If I try to connect these right now, everything's going in the same direction. That is a dead giveaway I've made a mistake. And my mistake was right here. That's supposed to be the point -1, -1. So that should have been a -1 there, that should have been -1 there. And then -1 minus 5, that should be the point 4, -6. So if I fix that, now I get that shape that I would expect. I graphed the wrong one, but let me try that one more time. 4, -6 would be here, and then the 2, -4 would be right here. And so now I get that shape that I would expect, that curve. Now, we did say the parent function looked like this one, right here. So why is it looking like this? Now remember, we had a reflection. So if it's reflecting, of course it's switching directions, right? But by knowing the shape of that parent function, the parent function shape's not all of a sudden going to switch to a parabola. It's not going to switch completely. It's still going to have the same basic shape. So we can use those parent functions, those ideas of those parent functions, to help us make sure that everything is in the right place. All right, let's do one last one of these. Let's take the parent function g of x is equal to -5, absolute value of x minus 2 plus 4. So we got a few different things going on here. First thing I want to do is identify my parent function as the square root of x. Next, I'm going to list transformations. So the keys are 1 and that last step. I'm not going to identify how many steps I have yet. Let's just identify the first and the last. First thing is always horizontal shifts. Look inside my parent function, I see a -2. Tells me I have to go right 2. Vertical shifts always occur on the outside, plus or minus. That's going to go up by 4. Now let's work on the inner steps. 2. Well, I see this -5 thing in front. Remember the 5, I'm going to ignore the negative on it. The 5 is telling me I have a vertical something or other, because it's on the outside. Because it is a 5 that is greater than 1, it's going to be a vertical stretch by 5. The negative is going to cause a reflection. Reflection over the x-axis. So now I'm going to set up a table with the square root of x points, and I'm going to try and get them right this time. 0, 0, 1, 1, and 4, 2. If I'm going to go right by 2, that means I'm taking my x's, adding to exactly the opposite of what it had told me to do in the initial equation. So I'm going to have 2, 0, 3, 1, and 6, 2. Next, I'm going to vertically stretch it by 5. That means I'm going to take the y's and multiply by 5. So we'll have 2, 0, 3, 5, and 6, 10. And then I'm going to go and reflect over the x-axis. And that means I'm making the y's negative, exactly what the initial problem had told me to do. Notice -5. Notice here I'm doing both the negative and the 5 at the same time. Remember how I said those inner steps didn't matter? We could actually combine these two steps into one if we wanted to. We could have done them at the exact same time because we're doing something to the y in both cases. The key is the horizontal and vertical motion's got to be broken off into its own. So we get 2, 0, 3, -5, and then 6, -10. And in the last step, we said we went up by 4. So that'd be y plus 4. So 2, 4, 3, -1, and then 6, -6. So these are the points I need to be plotting. 1, 2, 1, 2, 3, 4. There's my first point. 3, -1, and then 4, 5, 6. 1, 2, 3, 4, 5, 6. Try to hit that a little bit closer. Again, it is easier with graph paper. Now, we do have to remember that the square root is just a single ray, meaning it has that fixed endpoint, and it's going, that's probably a little exaggerated. One more time. There we go. Going just off from that one single point with the square root of x, we want to make sure we're not continuing through the other side. That would be incorrect. So there's how we can do transformations of our basic parent functions. What if we want to go the other direction? What if we're given the equation of the graph and we want to write down its equation? Well, now that we know what the transformations do, we can do that. If we simply relied on the calculator can't take a graph and write out the equation. So we can take a graph and we can write out its equation. We're going to do that in the next video. The other thing I want to do in the next video is look at non-traditional parent functions. Not everything is a perfect x squared or y cubed or x cubed or y equals square root of x. Some things are just crazy piecewise functions that kind of jump around. And so we want to be able to take those and transform them as well. It works the exact same way. So really, it's not going to be anything new there. So please do continue on to the next video.